Hi guys, Mrs. Valdivia. Today we're going to go on to chapter 3, atoms, using our Rebel chemistry textbook. So let's take a look at this image here. Where are the atoms located? Where do you guys see atoms? Do you see them in the air, in the rocks? Do you see them in the ocean, on the boat, in the sand? I see them everywhere. All around us, and everything we do and everything we touch, right? The things we see, the things we hear sometimes, even the things we smell and taste are composed of tiny little particles known as atoms. And those atoms themselves make up our fundamental elements. Okay, we have about 118 fundamental elements. 98% of those are naturally occurring. The rest are man-made elements. And the atom is the smallest unit of matter that makes up any element. Okay, so the atom's smallest unit of matter that makes up any element. Now, the atom itself is composed of different parts: the proton, the neutron, and the electron. Okay, we're going to talk further about those and what those unique properties do and how we use them in chemistry. The way that we create and produce different substances, not just us, I mean the world, right, naturally does it as well, is atoms combine together to form compounds and mixtures. So let's look here in the image again. Look at the air. What is the air composed of? In the air, we see that we have heterogeneous molecules. And we have diatomic, not heterogeneous, scratch that. We have diatomic molecule right here. Diatomic means that it comes in twos. In this one, we have two different atoms. So here, it's two atoms that are the same. Diatomic element right here, or molecule, two atoms that are exactly the same. In this case, we have three atoms. Two are the same, one of them is different. Okay, so this is not a diatomic molecule. It's going to be something else. It's a nice little compound. If we look at the red one, the double red, they're exactly the same. So this symbolizes that it is the same element. Okay, you have two atoms made up of the same element. So you have a diatomic molecule. Now let's get into something more complex. Let's look at the water. The water, we have H2O, right? Hydrogen and oxygen. All of these little red and white ones represent H2O, dihydrogen monoxide. And inside dihydrogen monoxide, we have other elements. I don't know what they are. I just know that there is at least two more elements inside of that water. Excuse me. The boat is made out of more complex carbon forms, and you could see that in this cyclic carbon form, united together to make this wood grain. Okay. Now, the word atom derives from the Greek word atomos, meaning invisible, right? Or indivisible. Indivisible means that you can no longer divide it by anything else. So the Greek philosopher Democritus, so if you can see his beautiful face right here, Democritus, he lived around 400 BCE. He argued that you could take something and cut it, you could take something and cut it into tiny, tiny little pieces. And you're going to get to a point where you can no longer divide that piece and still have the same substance. So he was smart beyond his years, wise beyond his years, right? I mean, to come up with the fact that there is an atom that he called atomos and that it is indivisible, then it's going to be the smallest thing that element, that particle can be made out of in 400 BCE. I mean, wow. What did we do with that knowledge? Absolutely nothing. Okay. It took hundreds of years for us to actually go into that, right? Because science was great for one part and then it fell throughout history, and it would come back up and then come back down depending on who ruled, right? Well, from the Ottomans, right, we developed it over the years, okay? And this idea remained dormant, right? Like I said, for hundreds and hundreds of years. And it was about actually 1700. And when we started building new technology where we were able to start seeing, right, using x-rays and whatnot, what structures really were from these molecules. In 1700, Antoine Lavoisier, I actually don't know how to pronounce his name. Okay, so Antoine, he cataloged a large number of chemical reactions. He observed that when a chemical change takes place, the total mass before and after the reaction is the same. We kind of already know that. We studied that, right? 2 plus 2 is equal to 4. So what you start with is the same as what you end with, mass-wise, right? You have to have an equality. Both sides of the equation must equal each other. So the law of conservation of mass states that in chemical reactions, matter is not created nor destroyed. Okay. So that's the law of conservation of mass developed in the 1700s. So an example that we have is going to be our hydrogen and oxygen. These react explosively and they form water. So hydrogen atoms and oxygen atoms combine and form water. So if I start off with 4 grams of hydrogen and 32 grams of oxygen, and I put it in a sealed vacuumed container, how much water am I expected to have? So how much water? Well, remember, this is an equality. So when I see this yield sign right here, hydrogen plus oxygen yields water, I'm going to think of this like an equal sign. So this is like my equal sign. 4 plus 32 is 36. So I'm going to produce 36 grams of water. So let's go ahead and look at this other example. If 16 grams of methane react with 64 grams of oxygen, 36 grams of water are produced. How many grams of carbon dioxide are produced in this reaction? All right, quite simple. It gave us everything. All we're going to do is say, well, how much do we have of each? How much methane? We have 16 grams of methane. How much oxygen? 64. So 16 plus 64 is equal to, well, I don't know how much carbon dioxide we have because it's asking me how many grams of carbon dioxide. So this is the same as saying X. It's your unknown. X plus 36. And all we're going to do is solve our equation. That's it. And you're going to end up with 44 grams of carbon dioxide. In the 1800s, so about 100 years later, John Dalton, he was an English school teacher. He used to be like this weather enthusiast. He would take the barometric pressure every single day. He would go outside and do the barometric pressures. And because of that, of all of his data that he collected, we were actually able to get a good weather analysis of the area that he was in for that time period and how it changed over the years. Well, Dalton created his theory, and in Dalton's theory, he stated elements are made of tiny, indivisible particles called atoms. The atoms of each element are unique. Atoms can join together in whole number ratios to form compounds. Atoms are unchanged in chemical reactions. So let's take a look at these and see what does that even mean. Elements are made of tiny, indivisible particles called atoms. Well, this one right here, this theory was proven wrong because we know that yes, Elements are made of tiny particles called atoms. That part is correct. What is incorrect is indivisible. Where did we prove that wrong? Where did we split an atom? Nuclear chemistry. So nuclear chemistry is the splitting of atoms. So fusion and fission reactions, right? That made this part of his theory incorrect. However, he had this part right. The atoms of each element are unique. Correct. So each element has unique atoms, right? So we know that hydrogen, its atom is composed of one proton, one electron. And it has isotopes that are made out of one proton, one electron, and one neutron, or two neutrons. Okay, so that's just an example, but that's unique to hydrogen. All right, atoms can join together in whole number ratios to form compounds. What this means is that two hydrogens, so for water, two hydrogens plus one oxygen form H2O. Right? That's whole number ratios. We don't see 1.5 hydrogen plus 0.5 oxygen formed together to form a 1.5 to 0.5. That's just weird, right? So whole numbers. Atoms are unchanged in chemical reactions. Okay, so mostly true. This is now, we're going to add the fact that atoms are unchanged in natural chemical reactions. And the reason I emphasize the word natural is because we still have nuclear chemistry. So atoms are unchanged in non-nuclear chemical reactions. Would be another way to phrase it. All right, so let's take some appreciation of Dalton's ideas and let's look at this example. Okay, so in this one, we're going to burn charcoal. And charcoal, we know, is basically composed of just carbon. And carbon reacts with oxygen in the air. And it forms a new compound known as carbon dioxide. So that's what we see here. Carbon, which is the charcoal, plus oxygen in the air. And we're going to add an ignition source. They're going to burn together to create the carbon dioxide. We know that carbon atoms are distinct from oxygen atoms, that they are very different from each other. Okay? And one carbon atom combines with two oxygen atoms to produce one molecule of carbon dioxide. So these combine in a 1-to-1 ratio to make one CO2. Now you're going to say, whoa, Mrs. Valdivia, what is happening here? Why are these two oxygens together? Okay, well, there is 7 diatomic elements in the periodic table. 7 diatomic elements. You're going to have hydrogen. You have hydrogen, oxygen, nitrogen, oxygen, fluorine, chlorine, iodine, and there's one more. I'm missing one more, but there's 7 of them. I'll remember the next one and I'll write it down for you guys. Okay. So that means in their natural state, they come in pairs of 2s. Okay, let's look at the fundamental ideas. So from our brief little history of understanding, we know that all matter is composed of atoms. The atoms of each element have unique characteristics and properties. In chemical reactions, atoms are not changed but combine in whole number ratios, and these ratios combine together to form compounds. All right, so we're going to see, can we actually see atoms? Okay. So in this image right here, there's actually a video out there that you could YouTube. It's called The Smallest Video, or yeah, I think it's called The Smallest Video Ever. and you YouTube it, and it actually shows you that these are atoms, okay, and they manipulate them and move them around through some sort of high magnetic resonance of some sort. I'm gonna have to look at it again. It's been a while since I've actually seen the video, but it's really, really cool how they did it. And if you watch the background video, I mean, it took them hours to move an atom. Now, these atoms are underneath uh, a thin sheet of metal. Okay, so they're underneath a thin sheet of metal. It's not like the atoms are popped out, just hanging out. And so this is a still picture of them. What was it called? Scanning tunneling microscope. Okay, so the technique is like a scanning tunneling microscope technique. So look that up. All right, so a more common technique though for actually looking at atoms, it's crystallography. So in X-ray crystallography, we usually use that to visualize our atoms, where they're at, how they're moving. So in this example, you could see the X-ray structure of painkiller, and this painkiller is aspirin. And we know the properties of the substance depends on how its atoms are arranged. So the ability to see atomic arrangements through X-ray crystallography helps us actually study diseases, develop new medicines, design new materials and new properties. Now, the reason it's important for us to actually see this is because their aspirin is one turn away. Like there's something called cis and trans. When you get to organic chemistry, you'll learn that. And if you flip one of the molecules over one way, it's no longer aspirin, it is something else. Okay. So let's see, how did the periodic table of elements even develop? All right, so in about 1860, there was only about 60 known elements. Okay, more and more were being discovered each year. Only 60 were known, and the scientists would make like races who could develop the best periodic table, right? And so at this point, everyone was submitting different periodic tables. You could Google periodic tables throughout history. They didn't look like our common periodic table. The common periodic table that we see was developed by the Russian scientist Dmitry Mendeleev. And he organized the periodic table based on atomic masses. He saw a trend and went, this must be the way. He also arranged elements with similar properties and put them together. So we have metals, metalloids, nonmetals. He put them, halogens, noble gases, all together, right? So one of the biggest examples that we have is in one of them, he put fluorine, chlorine, bromine, and iodine into one column because they all react the same way. And by doing this, he was also able to predict that we haven't discovered all the elements. And in his periodic table, when he submitted it, he left space for new elements to be discovered and to be added to the periodic table. Oh, here's the periodic table. Okay, this is the way that he arranged it. Now this one's obviously been filled. When he had his, most of the noble gases weren't there because they hadn't been discovered yet. And now that we have a periodic table, let's go over those 7 diatomic elements. So that means, remember, that means that they come in 2s naturally. So when you find them in Earth, in their natural state, you're going to find them in 2s. They eventually separate when you form compounds or when they dilute in water, whichever one, they'll separate. So you have hydrogen, you have nitrogen, oxygen, fluorine. So let's write those down. nitrogen, oxygen, fluorine. Then coming down right here in group 7, we have chlorine, bromine, and iodine. And the one I forgot earlier was actually bromine. So we have fluorine, chlorine, bromine, and iodine. These are the 7 diatomic elements, and something kind of neat about them is that they form a kind of like a backwards L. Or you could say a 7 plus the hydrogen, whichever one of those that help you remember those diatomic elements. Now remember, that's how you find them in their natural state, but they do break apart. Okay? They do break apart. All right, so let's talk about the arrangement of the periodic table. It's similar to a calendar, okay? So a calendar is a period in time, right? And periodic just means cyclical, so it repeats itself, right? So these rows right here repeat themselves, okay? We have rows and we have columns, okay? So you're gonna have rows and you're gonna have columns. Okay. Now these rows and columns are known as periods. So this is known as a period. And the columns right here are known as groups or families. So you could say groups or family. So groups and families, this means right here that they have the same characteristics, behavioral characteristics. They behave the same way. In a period, it means that they have similar, they're in the same energy level. So this is also our energy level. So they're in the same energy level. So that means that most of them are in the same energy shell. Now that only applies for the first couple because it gets weird, it jumps around, but we'll talk about that in chapter 4. So the periodic table, like I said, it's arranged very similar to what we saw in a calendar. You have your rows and you have your periods. Okay. So remember, a column is a group or a family, and they have similar properties. Okay, they have similar properties. All right, so let's look at this one right here. The periodic table uses an accepted set of 1- and 2-letter abbreviations. Now, that's something we're kind of used to seeing already. So example, carbon, the symbol for carbon is C. The symbol for magnesium is Mg. You notice that the first letter is capitalized, but the second is not. Calcium, capital C, lowercase a. That is intentional, and that is the correct way to do it. If you write magnesium like this, that is incorrect. Okay. If you write calcium like that, that is also incorrect. It must be capitalized the first and lowercase the second one. Now, most of these names and symbols, they are going to match like the name that we have. However, there's some that are not the same because the name and the symbol vary. So example, these ones right here, sodium, iron, copper, and lead, their symbols are based off their Latin names. So sodium is natrium, and natrium, Na, is where we got the symbol for sodium, Na. Iron used to be known as ferrum or ferros, and so it got the symbol Fe. Okay. Periodic table, going a little bit more into it. The main group on the tops, so these numbers right here, they represent the families. Family 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's your main group elements. These ones are going to be all in the same energy level. So, example, these are all energy level 2. Okay, these are all energy level 3. These are not all the same energy level here. So with our transitional elements, the energy levels change a little bit. So they're not the same. Same thing with the intertransitional elements. It changes. So here we start at energy level 4, and then once we hit the transitional elements, we bump back up to energy level 3. So we're at energy level 3 all throughout, and then boom, back to energy level 4. Okay. So same thing here. 5 bumps up to a energy level 4, goes all the way through, boom, back down to 5. And then you'll notice transitional elements pop in right here. And it does something a little bit similar. This one pops up 2 different spots. Okay. We'll go over that some more later during electron configurations. Okay. In the periodic table, metals lie to the left of the periodic table. So a couple properties, metals are solids at room temperature. They're molded into different shapes. They conduct heat and electricity. The transitional elements in columns 3 to 12, so the transitional elements, these ones right here, 3 to 12, okay, they're often just called transitional metals. Okay, so in transitional elements, we just say transitional metals, heavy metals. Those are the names that they get given. So they include common things like our iron and our copper. So you see copper, zinc, silver, gold, cadmium. These are our common metals. Iron. Okay. So little images of them. All right, non-metals. So the non-metals, you notice there's less of them. Mostly everything is a metal. They are located on the upper right side of the periodic table, but not including hydrogen. Hydrogen and helium are a little bit different. So row 1, group 1 right here, is a little bit different when it comes to the rules and patterns than the other elements. Okay. So this one has 1 proton, 1 electron, and this one has 2 protons, 2 electrons. It has a full energy shell, right? It doesn't fit its 8, sadly, but it still has a full energy shell. And because it's full, it behaves like a noble gas, so helium was added to the noble gas section. Hydrogen only has 1 electron. So that means it only has 1 valence electron. It does not behave like a noble gas, so it can't go here. It definitely doesn't behave like a halide or halogen, okay? So it doesn't go in these ones here. It behaves more like our alkaline metals, and so they put it in group 1. These ones right here, these are known as your metalloids. That means they behave as metals and non-metals. So they're great for electrical components. Okay. Group 1 is known as our alkali metals. They react very, very violently with water. So lithium, sodium, potassium, rubidium, cesium, francium, they react violently with water. They're very, very soft metals. You could cut them with a kitchen butter knife. The next one is your alkaline earth metals. And the alkaline earth metals are a little bit harder. They burn very, very brightly when you combine them with oxygen. They are less aggressive inside of water compared to group 1. Right here we have our halogens. So our halogens, fluorine, chlorine, bromine, iodine, okay, these ones right here react very, very quickly with all other metals and non-metals, and they form a diverse number of compounds. And you find them in almost everything. They are, I call them my more dangerous elements, okay, per se, especially in their natural state. Okay, so they're found as diatomics, and we went over that. There's 7 diatomics. Fluorine, chlorine, bromine, iodine are 4 of those 7. The last group is known as our noble gases. They generally don't react with other elements to form compounds. They have a full outer shell, so they are very happy just being noble and on their own. All right, so in about 1800s, John Dalton had articulated the ideas of the atomic theory. So we're just going to review really quick. He said that atoms of each element are unique. Correct. Atoms combine in whole number ratios to form compounds. Correct. Atoms are not created or destroyed in chemical reactions. Correct. What we start with is what we end with, mass-wise. Subatomic particles are particles that make up atoms. And we know that those subatomic particles are protons, neutrons, and electrons. All right, to describe your particles, mass is based on atomic mass units. It's usually abbreviated with a U or an AMU. AMU when we're talking about mass. 1 atomic mass unit is equal to like 1.66 times 10 to the negative 27 kilograms. That means it's a very, 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 very small number. What is charge? Okay, so charge affects how particles react with each other. Some particles have positive charges, some of them have negative charges. Particles with opposite charges attract each other. Okay, so opposite ends of charges attract each other. Similar ends repel each other, kind of like magnets, right? Opposites attract, similar repel against each other. All right, so the year that changed chemistry was 1800. With the scientist was Volta, Alexandro Volta, I believe, and he created the first battery, and he called it the electrochemical cell. So this is what the first battery looked like. Okay. I think he used pieces of metal soaked in like sulfuric acid, and he connected some wires together and charged it. Anyways, Alexandro Volta. So Volta, voltage comes from him, the word voltage, and that's the first battery. We know that it was a crucial milestone. In this experiment, they are electrically charging water, and they're seeing the separation of hydrogen and oxygen inside of water. So they have water in this cup, and they're electrifying it. As it electrifies, your water, which is H2O, breaks apart to give you hydrogen plus oxygen. Now you notice that one of these is more full of air than the other. So this one has more air and this one has less air. However, based on this equation, it looks like they're equal. Almost. This equation is not balanced. Okay? So in order to balance an equation, you have to have the same amount on both sides. Here I have two hydrogens, one oxygen, two oxygens. So that means that I have to put a number 2 here so that I can now have two oxygens. So two oxygens and two oxygens. That's good. My water, I have 2 times 2, which is 4. Here I only have 2. So I have to multiply this 2 by 2 to get 4. And now I'm done. So for every 2 molecules of water that break, I produce 2 diatomic elements of hydrogen and 1 diatomic element of oxygen. Therefore, I am producing more hydrogen. So I deduce that this is my hydrogen gas, H2, and this is going to be my oxygen gas, O2. Oh, look at that, correct. Okay, this one's just the image showing charged particles. Here's our particle source. They're going to move something through it, and you're going to see its attraction. So based on how this moved, I could see that it moved towards the positive side. It went up. Okay, so that means it was attracted to it. And you're saying, okay, what does that do? What do we know? Well, based on that, you can actually tell the charges on different particles. Like, what's the charge on this? What's the charge on that? During this time and times of more experimentation, we had J.J. Thomson, who actually even created the plum pudding model. And the plum pudding model is actually closer to the model, the actual model of an atom today than the Boyle atom. Okay, so J.J. Thomson discovered the electron using this experiment, or an experiment similar to this one. He used the cathode ray tube experiment. All right, so let's look at J.J. Thomson's plum pudding model. Okay, so in his model, he envisioned that the atom was similar to this, where all of the plums or the chocolate chips were positive particles. So this was all little positive particles, okay? And that all the small negative electrons were spread throughout the positive substance. So, yeah. Actually, I have that backwards. I apologize. Let's erase that. He said that all of these are negative charges. Okay, these are all negative charges, so they're all electrons. And that everything else that is not something inside this muffin is positively charged, right? So the dough, or bread in this case, is positively charged. Okay, this is the experiment Rutherford composed. When Rutherford did this experiment, he actually discovered the nucleus. This is called the gold foil experiment. And he discovered the nucleus through the gold foil experiment. So he took an alpha particle, he shot it through a thin piece of gold, and he noticed that some things went straight through and some got deviated depending on where the laser hit. Okay, so based on that, he noticed that every time it hit the center of something, that the line would spread away. Okay, it'd have its own It would just move away from it. And he deduced that the center was a very, very small condensed part inside of the atom that must have been positively charged. Why positively charged? Well, the ray he used is alpha particle. These alpha particles here are positively charged. They have a positive charge. So if you're shooting something and you hit something, if you're shooting something that's positive, it's all positive, and it hits something that's positive, well, if you have positive plus a positive, these are going to repel. They do not want to be together. Okay, so this is not going to work right here. Positive and positive or negative and negatives do not work. Opposite charges attract, similar charges repel. Okay, let's go ahead and talk about the properties of an atom. An atom is composed of a nucleus, electrons, and inside the nucleus you have neutrons and protons. Outside of the nucleus you have electrons. Okay. One might compare that the nucleus is the size of a mosquito and the atom is the size of a football stadium. That's how small the nucleus is that's inside of this super tiny small atom. So this part right here I'd say is nice to remember. Okay, the particle, the mass, and the charge. Now we round our masses. If you go to general chem, don't round your masses. You'll end up using this information to actually do your calculations. Okay. So this is only for our intro chem class. Protons, we're going to say, has a mass of 1, and its charge is positive 1. Neutrons have a mass of 1, and its charge is nothing. A neutron is neutral. So you hear that? A neutron is neutral. They don't have a charge. And electrons have a negative charge. So how do we identify what kind of atom we have? The number of protons determines the identity of the atom. So the periodic table is not only separated by mass number, it's also separated by proton numbers. So the first element, element number 1, is identified as having 1 proton, and that is going to be hydrogen. If you have something with 2 protons, that is going to be helium. 3 protons, lithium. That means they're all unique. They're all different. So in a periodic table, it's composed. The atomic number is the small number on the top, and the mass number is the number on the bottom. Now, the reason that we see the numbers in decimal form is because the numbers in the periodic table is the average weight of an atom, because we have isotopes. Okay. So mass number is the number of protons plus neutrons. All right, now let's go ahead and talk about isotopes. And actually, I'm going to take a quick break and come back. Okay, guys. All right, isotopes. So isotopes, it's possible for atoms to have the same atomic number, but a different mass number. So they can have the same atomic number, which is the number of protons, but they will have a different mass number. How is that even possible? Isotopes. Isotopes are atoms that have the same atomic number but a different mass number because they have different number of neutrons. So we're going to look at hydrogen. Okay. Hydrogen has 3 isotopes: protium, deuterium, and tritium. In protium, we have 1 proton, 1 electron. That is actually the most common way to find hydrogen, just like this in its protium form. Deuterium, you just added a neutron to it, 1 neutron, and now you have deuterium. D stands for 2. Your mass, your total mass is 2 AMUs. Here, your total mass is 1 AMU. Now, tritium. Tritium stands for 3, and we have our 1 proton plus 2 more neutrons. Add them together, we get a total of 3 as our atomic mass number. Okay. Writing a symbol. Here we go. So in our symbol, we have helium. On the top, mass number. On the bottom, atomic number. Actually, we switch it. Atomic number is usually on top, mass number is at the bottom in your periodic table. This format here is usually used for nuclear chemistry, but you'll see it like this in some textbooks. Make sure you understand which number is which. Okay. The whole number is always going to be your atomic number. Your mass number is most likely going to be in decimal format. So here, P plus N is protons plus neutrons. And atomic number is only protons. So helium is composed of 2 protons and 2 electrons. So when we write its symbol down, we're going to write He for helium and atomic number and mass number next to it. Okay, so remember, you're going to see it in 2 different ways. You might see it even like this: 2, 4 helium. And you're going to say, well, which one is which? Well, you're always going to see helium with a number 2 because it's always going to have 2 protons. If the number of protons changes, the element changes. And one more time. If the number of protons change, the element will change. Okay, here we go. An important isotope of uranium has 92 protons and 143 neutrons. Write the symbol with the atomic and mass numbers. Okay. So you're going to first start with the atomic symbol, which is U. Uranium is with a U. You want to apply the atomic number, which is 92. And then you want to find out, well, how much is it going to weigh? Okay. To find the mass number, all you do is add together the number of protons and neutrons. Add them together. So you'll have 92 plus 143. And that's going to equal to roughly 235. And you write that corner, you write that number on the upper left-hand corner. Okay, so just like that. Clean it up, box it up, whichever one you want to do. All right, so average atomic weight. In this example, imagine you have a dump truck full of poker chips. There are too many chips to count, but you know that 10% of the chips are $1 and 90% of the chips are $2. In order to find the average value of the chips, we multiply the value of A times the fraction of chips that are in A, plus the value of B. Okay, I know this sounds hard, but let's just look at the equation. All right, average value is equal to the value of A times the fraction of A plus the value of B times the fraction of B. And we get to find out what's the average value of chips. So right here it says 10% of the chips are $1 chips. So 10% turned into a decimal format, and they're only $1, so 1 times this 10%. Now that's only part of it. You'll notice that we have more. You have another one that says it's $2 per chips. So you're gonna have to do this one more time. Let's see. Excuse me. I think that's it for that one. Oh no, there was something I was gonna add. If there would have been more values here, like percent of this, of that, or something similar to this, don't freak out where you're like, oh, I could only put my answer once. You could put your answer however you could put it more than once. You could fix your answers. Yeah, if that doesn't make sense, how can I word this for you? If you have more than one, so scratch what I said. I apologize. Okay, I'm dozing off here. All right, if you have more than one form here, so like 10% is $1, 90% is $2, right? So this is your first set. This is your second set. What I was trying to say is that you can have a third set. Okay, so you can have a third set. You could have a fourth set, and all you're gonna do is turn your percentage to a decimal, multiply it by whatever, in this case, the money amount, and add them together, and that's the average value. So in this example, you're going to do exactly the same thing. You want to find out the average value. So you're going to take these and turn them into decimals by moving the decimal over twice. 1, 2, and this one you're going to move it twice. 1, 2, like that. Okay. You're going to multiply these numbers together, the 12 and the 0.98, and you're going to get something, I don't know what. The 13 times the 0.01, you're going to get something, I don't know what. So you get two different numbers, and you're going to add those two numbers together, and that's going to equal the average atomic mass of carbon. Okay. A quick review. A proton determines the identity of the atoms. The atomic number is the number of protons. The mass number is protons plus neutrons. Isotopes are the same number of protons with different neutrons. When writing symbols for atoms, we sometimes write the atomic number on the lower left-hand side of the atomic symbol. Okay? But you could always write it on the upper left-hand side. Electrons. A little quick preview of our electrons. Okay. So the electron is outside of the nucleus. It's not inside of the nucleus. And they have a negative charge, and they're very, very small. So in 1808, John Dalton published his atomic theory. That theory laid the foundation of all our modern work that we have now and all of our understanding of the atoms. I'm sure eventually we would have came up with something later on if Dalton wouldn't have been around, but he made life so much easier for all scientists. Right. So timeline, 1800, John Dalton's atomic theory, atoms are indivisible particles. Then later in the 1900s, we had the plum pudding model. So it stated that negative electrons are spread through a positive matrix, right? So The negative electrons are all in there, just kind of loosely moving around. Okay, review of the gold foil experiment in which the nucleus was discovered, that it was small, dense, and positively charged. The Bohr model. The Bohr model is the model that we use all the time. And we use it all the time because it's easy for us to visualize and to understand chemistry based off this Bohr model. The other models that we have, people are constantly getting lost in them or confused. They don't understand them, right? So especially the new modern model. And that's because the electrons are free moving in those models. But in the Bohr model, the electrons are not free moving. They're actually somewhere inside their electron cloud or their quantum model, which basically represents what we kind of represents a mixture of the most modern atom. Okay, so in this one, the electrons are somewhere inside of these lobes. Okay, they're somewhere inside of the lobes. Okay, so I think this is going to be the last part we're going to go over is ions. We went over isotopes, which means that it's an atom with the same number of protons, different neutrons. Now let's go into isotopes. Ions, an atom or group of atoms with an overall charge. What does that mean? That just means you have one atom with a negative charge or two atoms with a negative charge. That's what it means. Atoms can lose or gain electrons, and they pass those electrons to other atoms all the time. All the time. Okay. So here we have lithium batteries. And in this case, we have, oh, my mouse isn't working. We have 3 protons and 3 electrons. These ones end up forming 3 protons and 2 electrons only. So depending on what it was next to, those 2 electrons most likely jumped and went in, made a different molecule somewhere else. All right, let's go through this example. Sulfur has an atomic number of 16. Sulfur atoms commonly form sulfide ions, and these sulfide ions have a -2 charge. How many electrons are in the electron cloud of sulfide ion? Well, you won't know because the electron cloud is exposed to the air. It's not in a vacuum, so you won't know. Okay. And that ends our slideshow for chapter 3, atoms. I hope this was helpful and that the extra things I gave you will help you in your future assignments.